Effective oil spill recovery in naval harbors depends upon a number of different factors. This film report documents the consideration of those factors during field tests performed in June of 1972 at the San Diego Naval Station. These tests, sponsored by the Naval Facilities Engineering Command, evaluated the operational status of Navy personnel, equipment, and procedures during several oil spill recovery operations. The tests also identified additional requirements that must be implemented before an effective Navy-wide spill recovery system can be achieved. Factors which affect the use of an oil spill recovery system can be grouped into three broad categories: personnel and craft requirements, equipment performance, and operational procedures. These three categories were investigated during controlled spill tests using Environmental Protection Agency approved purposeful oil discharges, both inside the San Diego Naval Station harbor and in an open water area 7 miles off the California coast. Equipment components for an oil spill recovery system include containment, removal, storage and transfer, and oil-water separation. The June 1972 tests evaluated only the containment and removal components. The storage, transfer, and separation component requirements were not critical for the small controlled spills involved in these tests. One of the key elements in a recovery operation is the oil removal device. The 7-foot-long by 4-foot in diameter device used in these tests consists of 41 vertical aluminum discs. As the discs rotate, the oil adheres to their sides and is brought over the top where it is wiped off by stationary vertical wipers. The wipers are situated over a central open trough through which the oil drops and is transferred into an onboard storage tank. The oil removal device was installed in a specially modified Navy LCM and was evaluated in both quiescent harbors and in offshore environments. In the confined harbor environment, it was found that Navy mil-spec Type 1 containment boom was of sufficient size and strength to provide oil slick containment. Its relatively light weight and ease of handling enabled the complete encirclement of a small slick. The boom could then manually be hauled back into the boat, and in doing so, would draw the oil slick into the oil removal device. In the offshore environment, it was necessary to use a mil-spec Type 2 containment boom. Because Type 2 is 3 times as large and as heavy as Type 1, it was very difficult to deploy manually. With its heavy weight and bulkiness, many of the fabric handles were torn loose, and many tears were caused by dragging the boom over rough surfaces during deployment. Deploying and retrieving boom over the lowered bow ramp of the boat proved to be a definite hazard to the crew, especially in choppy seas. All this indicates the necessity of developing a mechanical deployment and retrieval device for handling Type 2 containment booms. Both boom sizes suffered from the lack of adequate boat boom connectors and from the lack of buoyant tow assemblies. In the harbor test, using Type 1 booms, fire hoses were needed to prevent leakage of test oil from around the ends of the boom. This problem can be alleviated by the addition of bulkhead attachers. In one case during the offshore test, the lack of an adequate towing assembly resulted in a boom breaking away from the tow craft. Personnel and craft requirements for removing the most common Navy oil spills, those occurring within a confined harbor area, are less extensive than for the larger spills occurring in open water areas. In a quiescent harbor area recovery test, a six-man work crew supervised by a Navy chief had little difficulty using the disc-type oil removal device and 200 feet of Type 1 boom to recover a 100-gallon test spill of Navy Special Fuel Oil, NSFO. During the operation, test data was routinely gathered by project engineers. Collection rates varied from 2 to 6 gallons per minute, and water content ranged from 40 to 60%. Approximately 33% of the oil passed under the removal device and was not collected, a very low throughput efficiency rate. Offshore oil spills require a great deal more equipment and personnel than a quiescent water situation. In the June test, a minimum of 6 Navy craft and crew were used to recover a 25-gallon spill. A 2 LCM team, one with an oil removing device, the other towing an attached 200-foot Type 2 boom, were the primary oil recovery craft. To ensure environmental safety, a second team of 2 LCMs, also capable of recovering oil, stretched an 800-foot safety boom across the downwind side of the test area. A yard-class tugboat acted as an observation platform and surface command center. A PBR river patrol boat was on hand to perform a variety of miscellaneous tasks. A helicopter overhead provided aerial surveillance and an airborne camera platform. After discharging 25 gallons of NSFO, the slick was allowed to spread for 15 minutes. The PBR then encircled the entire slick with less than half a cup of sorbitan monoleate, a non-toxic chemical supplied by the Naval Research Laboratory. Commonly known as piston film, sorbitan monoleate is utilized to contract oil slicks for easier removal. In this case, the area of the slick was reduced by 68%. During the in-harbor test, the chemical caused a reduction of 50%. Although piston film is used on all oil spills, it is especially important in the open water, where spills tend to be larger and the nature of the sea prevents complete encirclement by booms. In these cases, the initial job of containment has to be accomplished by chemical means. The first part of the test procedure called for the primary recovery boat to pass through the slick and evaluate the feasibility of a single boat recovery system. With forward speed ranging from 0 to 2 knots, a flow rate of approximately 2 gallons per minute was maintained. Output samples showed a very high 75 to 98% water content. The trail of oil behind the boat after it exits the slick is a graphic example of the low throughput efficiency rate of this type of oil recovery device. Later, the boom towing LCM linked up with the recovery boat and they established a J configuration with the boom. In this configuration, the oil would angle into the mouth of the recovery device as the boom was dragged through the slick. In actual practice, however, it proved quite difficult to maintain the J configuration, indicating that a great deal of practice and some refinement of procedures will be required before this method can become operationally feasible. During the open water test, it was discovered that overall observation, as well as command and control functions, were very difficult to perform from a surface-level platform. The only craft giving sufficient overall visibility was the airborne helicopter. The tests documented by this film and a companion written report with complete technical details are only part of a continuing effort to solve the oil spill problem. It is only with comprehensive development programs, like those currently underway at the Naval Civil Engineering Laboratory, that we will ultimately achieve an operational naval harbor oil spill recovery system.